So let me start. Welcome everyone to BCast, which is a bi-weekly series of scientific presentations regarding high-performance computing organized by the Scalable Computing Laboratory at ETH Zurich. Today, we have with us Abhinav Bhatele. He is an associate professor at the University of Maryland, where he is the director of the Power Software and Systems Group. Abhinav has received Best Paper Awards at Europar 2009, IPDPS 2013, and 2016. He was also selected a recipient of the IEEE TCSC Young Achievers in Scalable Computing Award in 2014, the LLN Young Achievers, the LLL Early and Mid-Career Recognition Award in 2018, and the NSF Career Award in 2021. He's an associate editor of the IEEE Transactions on Parallel and Distributed Systems, and he's one of the general chairs of the IEEE Cluster 2022 and research papers chairs of the ISC 2023. Abhinav will give us a presentation, and then we'll have a Q&A session afterwards. So without further ado, please take it from here, Abhinav.
Thanks, Marcin. Hey, hello everyone. My name is Abhinav Bhatele. I'm a professor in the CS department at Maryland. And first, I want to thank Torsten, Marcin, and SPCL for inviting me to give this talk at the SPCL BCast seminar. Today, I'm going to talk about the fields of high-performance computing and artificial intelligence and machine learning, and the synergistic relationship between them, and some research that we are doing in my group in these areas. In the last decade, we saw a big data revolution. There was a lot of, an insane amount of data coming from various places, and people were doing a lot of data analytics on this data to gain knowledge from this data. In this current decade, we are going through what we can call a digital revolution or a renaissance period for AI and machine learning. And there have been various factors that are leading to this ongoing revolution. First, the availability and curation of high quality data sets such as ImageNet, interfaces such as Hugging Face, where you can download them, upload them for other people to use, and so on. Improvements in GPU architectures. They have more memory now, faster data movement between CPU and GPU, across GPUs, and so on. And then also we have an availability of open source software such as TensorFlow, PyTorch, and so many others that can help you train your deep learning models and use them for inferencing. Now, all of these have led to an improvement in AI architectures and also the development of novel methods that can help you improve your statistical performance of the neural networks. As all of this is happening, people in the high performance community have been wondering about the convergence of AI and HPC. So this quote is from a recent white paper from some people at Illinois and other places by Huerta et al. And it includes people, well-known people in HPC, such as Bill Grob. There's an interesting quote in that which says, to date, there is no rigorous framework to constrain the ideal set of hyperparameters that ensures rapid convergence and optimal performance of AI models as the number of GPU nodes is increased to accelerate training. Of course, this is 2 years old. The field of AI and HPC, they are moving fast, but I still see there are several interesting research problems in this space. So just looking at that quote here, there are two separate research problems when we think about training in AI. One problem is finding the ideal set of hyperparameters that would lead to very good statistical performance, just statistical efficiency, and lead to rapid convergence of your AI models. The second separate problem is if you have access to a large number of GPUs or GPU nodes, how do you scale your training to a large number of GPUs? Now, if we look at the other direction, if we want to use AI and machine learning and high performance computing, there are various use cases for it. You can use AI and ML to optimize system performance, individual application performance. People are also using AI and ML to improve simulation and modeling when they are working with computational science codes by taking some parts of your physics, replacing it with an AI model, and seeing if you get similar accuracies. So what I see, it's unclear whether the fields of AI and HPC and the hardware for AI and HPC are going to converge. But I definitely see that there's a synergistic relationship between these two areas. And in this talk, I'll talk about some work we are doing in this area, both applying HPC for ML or AI and ML, and then applying AI and ML to HPC data. So I'll start with the first part, which is our work on scaling the training of deep neural networks on large-scale HPC systems. And then I'll talk about how do we use AI and ML methods to create these data-driven models that use HPC data. So probably several of you are already aware of deep neural networks, but I'll provide a brief background just to get everyone on the same page. Deep learning is an area of machine learning that uses artificial neural networks to learn complex functions. These are the data is often high dimensional, from text, images, audio, sometimes multiple sources, and so on. And we have seen a widespread use of deep learning in computer vision, natural language processing, and so many other fields now. Now, neural networks can be used to model complex functions. This is showing a single neuron. You have some inputs, you apply some weights to them, then do a summation, apply some bias, and then you pass that through an activation function to get some output. You connect many such neurons together, that creates a single layer. And when you connect many such layers together, you create a deep neural network. There's an input layer, several hidden layers, and then an output layer. All these several layers in a deep neural network process batches of the input data and goes from the input layer all the way to the output to do some prediction or modeling task that you had in mind. The problem that we are trying to solve when training a neural network is to find a set of weights or parameters that best fit the function we are trying to learn over a given training set. So in this example, if we have certain images that are in different classes, what we want is the neural network to learn based on the training data set and to be able to classify an unseen image into one of these classes. And the goal is to find the sets of weights or parameters for each of these layers, so the theta 0, theta 1, and so on. Now, in the past few years, people have realized that you can use parallel or distributed training and exploit parallelism in training of neural networks. If you look at the plot on the right, starting from 2012, and now if you look at the past few years, the number of parameters in deep neural networks has been increasing significantly. We have gone from, tens of millions to billions of parameters or tens of billions of parameters on commodity hardware. As we'll see, as I'll describe in the next few slides, there are many opportunities for exploiting parallelism. First, there's an iterative process we are doing. We go through epochs in the training, and maybe we can parallelize those. There are many iterations per epoch where we do work on mini batches, which are shards of batches. And then there are many layers in a deep neural network. Maybe we can parallelize over layers, right? So broadly, we can classify the different techniques or methods for distributed neural network training into three kinds. And I'll probably not spend a lot of time on them, but do a quick overview and then talk about the work we are doing in this area. So the first most basic method for parallelizing DL training is to use what we call data parallelism. You can divide the training data among many workers. If you have GPUs, you can consider each GPU as a worker. So in the figure on the right here, we have 4 GPUs. Each GPU can work on different data. 1, 2, 3, 4 is signifying different data, and each GPU takes that data through a forward pass and a backward pass, and then you start processing the next batch and so on. Now, in this case, when you use data parallelism, each worker has a full copy of the neural network and processes different mini batches. Once every GPU is done with processing one batch, you do an all reduce operation to synchronize the gradients, because everyone has a copy of the network and you want the copies to be synchronized. And then you move on and you keep doing this. Some popular examples of data parallelism are PyTorch's GDP, Zero, which is a framework from Microsoft, and they can both be used for data parallelism. Now, an obvious problem with data parallelism is that if your model does not fit in a single GPU, you are out of luck. Marcin, I see a few people waiting in the waiting room. Okay, so the next method would be what people call intra-layer parallelism. So let's say your model does not fit on a single GPU. You probably want to split that model across multiple GPUs and train. In this case, you distribute the work within individual layers of a deep neural network between multiple GPUs or across multiple GPUs. This is also referred to as model or tensor parallelism, since essentially you're taking those tensor computations that would have ideally happened on a single GPU and splitting that work across multiple GPUs. Megatron LM from NVIDIA is a popular tool or framework for using model parallelism. The third kind of parallelism, which is probably less explored than the first two, is what we call interlayer parallelism. Now, as we saw in one of the initial figures, there are multiple layers in a deep neural network, and potentially you could divide these layers among different GPUs while keeping one individual layer on a single GPU, and do some parallelization in that dimension. Now, you might think that if you have different layers on different GPUs, there is a sequential bottleneck because a batch has to go through one layer before the next layer can start processing the outputs of the previous layer. To overcome this problem, we use a standard technique, a technique that's standard in architecture, which is pipelining, which is why this is also referred to as pipeline parallelism. You create a pipeline of mini batches that go through various GPUs. So while GPU 1 or while GPU 0 starts on the next batch, that is batch 1, GPU 1 can be processing the previous batch through its forward pass and so on. Now, this pipelining of mini batches helps us do concurrent execution. However, when you use pipeline parallelism, you have to do point-to-point communication because you need to communicate activations and gradients across the various GPUs that are managing different layers. So there's different kinds of communication happening in the different kinds of parallelism, and each has its pros and cons when you try to use those for parallelizing DL networks. Finally, more recently, many of the popular frameworks such as Megatron and DeepSpeed and the framework that I'm going to talk about have been combining multiple of these approaches together, sometimes combining all three together to use what we call 3D parallelism. And people have seen that if you use all the dimensions of parallelism, you can scale your training to much larger number of GPUs. Now, this is all great. People have done this before, but what are the problems in existing implementations? So recently, when we started, maybe 2 years ago, when we started looking at this problem, we realized that there were two issues. One, many of these implementations do not exploit asynchrony. Now, this sounds surprising from an HPC point of view. Non-blocking communication has been an MPI now for a long time, but many of these implementations still use blocking communication. The other thing that these implementations do not exploit is adaptivity. They use fixed scheduling. So they'll do one forward pass and then a backward pass and then a forward pass and a backward pass. So it's a very static kind of scheduling. And we felt that if we can exploit both of these, if we can exploit adaptivity and if we can exploit asynchrony, we can get much better hardware performance for the training of our neural networks while maintaining the same statistical performance. So which is what I'm going to talk about in the first part of my talk. We have developed a framework called AxoNN, which is an asynchronous message-driven framework. This work was published last year at IPDPS. So I'm going to talk about 2D parallelism, which is interlayer or pipeline plus data. However, recently we have added tensor parallelism also to AxoNN, so we can do 3D parallelism depending on the models you might be training and if you require 3D parallelism. So let's say we have 6 GPUs and we want to do 2D parallelization. You can decide how many GPUs to allocate for data parallelism and how many to allocate for interlayer or pipeline parallelism. So let's say we'll do data parallelism across 3 GPUs and interlayer parallelism across 2 GPUs. Once you have a batch, you split that into multiple shards. Each shard is processed by a different GPU. This is the part that's data parallel. Then when we think about interlayer parallelism, let's say you have 4 layers in your deep neural network. You take 2 of those layers, put them on the first column of GPUs, and the other next 2 layers and put them on the second column of GPUs. Now, when we say put them on the first column, each of those, each GPU in the first column has a full copy of those layers, because this is data parallelism. If you look within a column, but if you look across the columns, the first column has 2 layers and the second column has 2 layers. So this is a hybrid. By decomposing your number of GPUs in 2 dimensions, you're doing a hybrid between data and interlayer parallelism. Now, how does the, and this is at a very high level, but how does the training process work in Axon and in other models that use 2D parallelism? First, the GPUs read in the different shards. You do your data parallelism, do your tensor computations. Then in the interlayer parallel phase, where the layers on the boundaries have to communicate, you are doing a forward and backward pass. At this point, you do point-to-point communications to send your activations and gradients. And finally, when you're done with that, you do a all reduce within each column to conclude the data parallel phase. This is where you synchronize your local gradients in the data parallel phase. And finally, you run the optimizer. This can be run locally on each GPU to update the parameters. Now, like I was saying, if you think about interlayer parallelism naively, you might think that we cannot have parallelism because the subsequent layers have to wait for the previous layers. But you can use pipelining, where you can break a shard further into micro batches. And while one GPU is working on a subsequent batch, another GPU can be working on a previous batch, right? Of course, pipelining leads to bubbles. As you can see, there are some holes in this timeline here where we aren't doing any work. But let's say in a steady state, you have few bubbles and you can get a lot of work done using this pipeline parallelism. So now, as I was saying, so far, this has been done in other models, but the problems are that we don't have asynchrony and we don't have adaptivity. So one thing we noticed when we were comparing the NVIDIA Nickel communication library with MPI is that for point-to-point communication, if you use non-blocking MPI, that can be much faster than Nickel. So what the plot here is showing that the blue lines, the solid lines are MPI, the hashed lines are Nickel, and what we see, this is time on the y-axis. So we see that solid lines perform better compared to the Nickel lines. Now, for collective communication, Nickel is still better than MPI, as we see on the plot on the right. So we choose the messaging library depending on the communication. When we have to do collective communication, we still use Nickel. When we have to do point-to-point communication, we use MPI. So that's our first optimization we did in our custom framework, which we call Axon. We use asynchronous point-to-point communication. By doing this on a GPU, the computation on a micro batch can be overlapped with communication. Axon uses MPI isends and I receives, and wherever possible, for example, when we are running on NVIDIA GPU-based platforms, we use a CUDA-aware MPI that can use GPU direct to do direct messaging or direct copying of data between GPUs. That helps us get significantly better performance compared to using Nickel for the communication. In the next few slides, I'll talk about some other synchronized optimizations we have done. Like I was saying, the other thing we wanted to explore was adaptivity. This is something we got inspiration from Charm++, which is a programming model, a message-driven asynchronous programming model. And we realized that you could overlap computation with communication by using a message-driven scheduler and process whatever messages have already arrived and let those batches or the work for those batches proceed while we are waiting for other messages. So as I was saying, current DL frameworks use static scheduling when they implement pipelining. Each GPU alternates between processing a forward pass and then a backward pass on a micro batch. Axon implements a message-driven scheduler in Python. We post MPI I receives early on, and then we do an MPI wait any to wait for any messages that might arrive. Depending on where the message is coming from, we can figure out what batch or task is it destined for, and then we can start the computation for that particular batch. By doing this, we're able to schedule these forward and backward passes for a given micro batch. Depending on when the message is received, We don't necessarily wait for messages for a particular microbatch to arrive, and then we sit idle until that happens. So again, this message-driven scheduling and asynchrony helps us gain more performance. The next two things were more specific to the kinds of models we were training at that point last year. So one thing we noticed was that if we can reduce the number of GPUs we are using for the interlayer or the pipeline parallelism stage, we can get better, we can have lower communication, and which would lead to a lower communication to computation ratio. So this is what this plot is showing. If you're, since we are dividing the total number of GPUs into G data and G inter, if we can reduce G inter, we are getting better performance. Now, when you reduce G inter, you would be putting more layers on each GPU that would require more memory usage and so on, right? So how do we reduce memory consumption? One way to reduce memory consumption is to move some of the data in your training to the CPU. So in this case, one optimization we tried was moving the optimizer data, which is about 80% of the model state, to the CPU. And of course, we did some optimizations where, we compute the data in buckets and so on. But by doing this, we were able to get 5x memory savings, and we were able to reduce G inter and use the freed up GPUs for G data or more data parallelism. That helps us both with, reducing memory, but also optimizing communication. Now, a potential problem with this approach where you're copying data to the CPU is these CPU-GPU transfer overheads, because now you have to constantly transfer data back and forth. To minimize the impact of these overheads, we overlap the optimizer phase with the all reduce, and that helps us, lower the overheads with using the scheme of moving data to the CPU. Okay, so now we applied all of these optimizations to our parallel framework. Axon is written using Python plus MPI and Nickel. For the sequential computation or for the kernels or tensor computations, it uses PyTorch. We try to provide a PyTorch-like API, so you can, use as you would have trained your sequential models, or code similar to your sequential models can be used for training something in parallel using Axon. The plot here is showing the execution times or expected training times if we extrapolate to the full training time by looking at times per iteration or per epoch. And in this case, we are showing weak scaling. So we run 4 different models of different sizes. One is a 12 billion parameter model, and then 24, and then 50 and 100 billion parameters at 384 GPUs. And we compare our performance for Axon with DeepSpeed and Megatron. As you can see, compared to Megatron, we are significantly faster. But even compared to DeepSpeed, which is a highly scalable framework from Microsoft, I believe we're about 50% faster, 15% faster when we run at the higher end. This is just showing the same plot, but if you invert it and look at the percentage of peak flops. Now, as you might be aware, DL training is flops heavy. So as opposed to computational science apps, we can get a very high percentage of peak. And you see here that we get anywhere between, close to 55 to 45% of peak when we use Axon on training on, and these are V100 GPUs on training on NVIDIA V100 GPUs. Okay, so now let me also mention a few other optimizations you can do in our framework depending on different things or different kinds of training methods you're using. I am going to talk about one of those, but of course, there are other cases. For example, if you're using mixture of experts, you can do some optimizations exploiting that and so on. Now, this work is going to appear in IPDPS this year. And this worked, and recently we looked at pruning approaches, such as the lottery ticket hypothesis, which has become popular recently. And these approaches have shown that you can prune the neural network, basically zero down the weights that are close to zero, up to 80 to 90% without sacrificing statistical efficiency. So you can get this, you can get the same statistical performance from your neural network whilst working with a neural network that is, reduced in size by 80 to 90%. Now, this has huge implications for DL inference, because now if you can have a smaller model, you can fit that on a much smaller device, on edge devices, on your laptop, on your phone, and so on, and do this. Now, what we were considering is from a systems or HPC perspective, how can we exploit this sparsity when you prune neural networks and use that to optimize performance? So the plot here is just showing the performance of sparse libraries versus using a dense version, the CU BLAST version of them. What this shows is that if you use sparse libraries for doing computations on sparse tensors, you do not get good performance. So we wanted to see if we still do the computation in on dense tensors, can we still do some performance optimizations, knowing that we have sparse neural networks. So the optimizations we did in Axon were, first, we store some of the model state in sparse while storing other model states still in dense. When we do that, we reduce the amount of memory consumption. So we are able to further reduce G-inter, or the number of GPUs we use for the pipeline parallelism. That decreases bubble time, that also optimizes point-to-point communication. Of course, again, we do all of the computation in dense because, as we saw in the previous slide, CU BLAST is the fastest. So all of the computation is done in dense, but we store some model states in sparse, and we switch between sparse and dense as needed. As you will see in the performance results, even though we have overheads because of this switching, by reducing G-inter, we are able to get performance boost that offset the overheads we have of doing the switches. Second, since we know that we have sparse tensors, we now do the all reduce in the data parallel stage in a sparse format. What this lets us do is, you don't send zeros on the network, you're sending much smaller messages, and your communication is much faster. Using all of these improvements, we are able to significantly improve the execution time for Axon, and the second version is called Axon++ here. What you'll see is that the time spent in the green, the blue, and the pink, which is all communication. The blue is the pipeline bubble, that reduces. The time spent in the bubbles in the pipeline reduces, but also the time spent both in the point-to-point communication, which is the green, and the collective communication, which is in pink, reduces. So by applying this optimization and exploiting sparsity, we're able to get better performance. Now, this is for a different model, so this is not the same peak flops, but what we see here is that this is for 2.7 billion GPT-3 model. The Axon++ has better throughput than Axon, and of course better than deep speed that we had seen before. So what this is saying is that depending on the specific models you are training, you can also do further system optimizations. So there's a lot of opportunities for collaboration between AI and HPC researchers to help improve the scaling and optimize performance. Now I'm going to switch tracks here and talk a little bit about AI and ML methods and how they can help HPC. In the first part of the talk, we looked at how can we can help HPC, how HPC and distributed systems can help AI and ML in improving scaling performance. Now, very recently, let me see if I should move to the next slide. Okay, yeah, let's start with this slide. So one problem that I have been working in my group for more than a decade now is performance variability. Now, this is a recent plot from 2020 that shows when you run the same applications, and there are 4 applications here: Milk, AMG, UMT, and MiniVite. If you run the same executable with the same input parameters on different days, and this is on the Cori system at Lawrence Berkeley, you get different execution times or different performance. What this is saying is there's a huge performance variability on Cori, which can impact your software development cycle. It impacts how much time you request for your jobs and so on. So there's significant downstream impacts on the developer or the person using the machine if there is performance variability. A lot of this variability comes because on most HPC systems or supercomputers or clusters, there are 2 shared resources, the network and the file system, that is shared across all the jobs. So if there are some jobs that are either IO intensive or communication intensive, they can overload the network or the file system, and that can impact the performance of other jobs. Now, as I was saying, in the past few years, we have had an explosion in the amount of data we collect on HPC systems. Several Department of Energy labs, such as Lawrence Berkeley, Livermore, Argonne, they use a library called LDMS, which stands for Lightweight Distributed Monitoring Service, to record monitoring data on HPC systems. You can collect a vast quantity of rich but noisy data. You can collect network switch data about the number of packets going through your network, stalls, and so on. You can collect on-node data, floating point operations, cache misses and hits, and so on. You can also collect file system data, power data, cooling data, facilities data, temperature sensors, humidity, and so on. The question is, what can we do with all of this data? Can we use this data to optimize the system performance and maybe even optimize individual job performance? So that's what I'll briefly cover this. This is again a paper that was published at IPDPS last year. And if you're interested, you can look at the paper for more details. Now, the first thing we did was we wanted maybe less noisy data. So we did some controlled experiments on a system at Lawrence Livermore called Quartz. We ran 7 different proxy apps. They have very different communication and computation behaviors. And we ran each app several times a day for a period of, I think, 6-7 months. Once we had this data, we wanted to understand performance variability and see if we can create a machine learning model that can help us predict variability for future jobs. So the first thing we did was, with all the data we had, and just very briefly, we were collecting several performance counters from different sources. So you have sysclass IB for InfiniBand counters, OPA for OmniPath switch counters. You can get Lustre client counters for the file system data, or how much IO reads and writes you're doing. And then we also ran some MPI benchmarks to look at what's the current state of the network. With all of this data, we trained a classifier, AdaBoost, to predict if an app will experience variation. The inputs to this classifier were the system data that's in the table below, but also the job description. So the job description would be, we would assess the classifier by saying if an application is compute intensive or communication intensive or IO intensive, and so on. And the output of the model was, if for an unseen app, if we would expect variation, it would output 1. If we would not expect variation, it would output 0. Now, the question is, if there have been several papers, in fact, from our group on training such models that can model and then predict performance for an application. The question is, how can we use this information? So actually, let me go over this slide, and then I'll talk about how do we use this information. So this is just showing the performance of our classifier. We trained many different classifiers. In this case, we're showing 4 on the x-axis. And we see for most of them, we actually get very good F1 scores for using the system data to predict if an application will suffer from variability. Now, how can we use all of this information? We can potentially use this information in a job scheduler. When there are new incoming jobs in the queue, and let's say we know their something about their characteristics, like if it's compute bound or communication bound, we can use our model to predict if this application will see variability or not. If we think that if the model predicts that this application that's just sitting in the job queue is going to get impacted by variability, the job scheduler can decide to not schedule this job right now, maybe schedule other jobs that will have less variability, and then come back to this application later once the machine is less congested. So this is a high-level overview of our resource utilization aware job scheduler, which we're calling Rush. The inputs to this scheduler are, or the model plus scheduler are, 1, the system data. So we can train the model, the proxy apps data, and the benchmarks data. We use this to predict variability for our applications. We train the model offline, and then we pass on this trained model to the job scheduler. At runtime, when the job scheduler has to make decisions, it uses the trained model, the current job queue, and the current system information, the current counters for the system, to decide if a new job in the queue is going to suffer from variability. And like I was saying, if we think there will be variability, we don't schedule that job right now. So this is a sort of a pseudocode or high-level overview of the algorithm. We obtain recent values of system counters. We predict if the next job in the queue will experience variability. If yes, we put this job back in the queue, try to schedule the next job. Of course, we limit the number of skips of a given job to prevent starvation. At some point, if the job has been skipped enough times, we still go ahead and schedule it. The key idea here is if there are enough jobs that are not communication intensive, and we expect that they will not suffer from variability, we go ahead and schedule them, and we let the other jobs that are more communication or IO intensive wait in the queue. Once the system is less congested, or we expect there'll be less variability, we go ahead and then schedule those jobs. The way we tested our scheme was by leveraging the Flux scheduler framework developed in Lawrence Livermore. We actually did this on a real system. The Flux scheduler enables us to run a scheduler within a job partition, so sort of a hierarchical scheduler. So we did a large allocation on Quartz, which is a system at Livermore. And within that allocation, we ran lots of jobs using Flux. And then we tried the default scheme and the new rush-based scheme to see how things would work. The default scheme was just first come, first serve. And we looked at various workloads and how the scheduler impacts performance of future jobs. So the first plot here is showing the number of jobs that actually see variation when we use our new scheduler. And what we see is that the average case, or the average number of jobs that see variation for the different applications, goes down significantly, especially for some applications that are communication intensive, such as Lagos, AMG, and SW4 Lite. But more importantly, the maximum number of jobs that see variation also goes down, right? So we are able to limit the number of jobs that are seeing variation, which is a good thing. Now there are fewer jobs with variation when we use the new scheduler. Of course, people might also want to know that by how much do we improve the actual execution time. So again, like different jobs, execution time improves by different amounts. So what we see is for some of the applications that are more communication intensive, such as Lagos and Elban, the maximum communication time comes down by up to 4 to 5%. And actually SW4 Lite also comes down by 5.8%. For other jobs, we might bring the communication time down by a smaller amount, but we don't make any negative performance impacts on these applications, so it's still good. Now, again, a natural question might be, we are making some jobs wait in the queue for longer than they would have normally waited, right? So why would people be willing to do that? I think one reason is if many people like to see their jobs being more predictable, especially when they're trying to do performance debugging, or they're making a change in the code and they want to see how, if the change improves performance. And oftentimes people are not waiting around and sitting and looking at the job queue, waiting for their job to run. People submit jobs, they go away, come back later and look if their job has run, right? So for most users, even if the job has to wait longer, but it gives you more predictable performance, that's a good thing. However, like looking at here, we are comparing the make span of running an entire job trace through the system. We see that we don't even increase the jobs, the make span significantly. What you can see is, in fact, we improved the make span in most cases for the different workloads we tested, which is on the x-axis. So we are either keeping the make span constant or improving the make span, because each job now runs faster and has less variability. In terms of the wait times per job, what you'll notice here is that for some applications that are communication intensive, such as Lagos, AMG, SW4 Lite, since they are waiting longer, we actually increase their wait time by a small amount. This is only in minutes. So if your job had to wait for 12.1 minutes, it's now waiting for 12.8 minutes. So it's not significant. And for other jobs that get scheduled automatically, it basically makes no difference in time. So overall, like using this job scheduler, we can improve the predictability of individual jobs while not making any impact on make span, and also just having minimal impacts on the average wait time. So in most cases, this is a win-to-win situation, and you solve this problem of performance variability at a system level. Again, as a reminder, the key thing here is we trained an AI-driven model, or a data-driven AI model, and that helps us predict variability in a new job, and that helps us do these optimizations in a job scheduler. So this is a good example of how AI can help HPC systems in improving efficiency. Now, the other thing, I think I still have a few minutes, so I'll talk very briefly about another new area we are working in. This is still work in progress, so it's very new. You might have noticed that large language models are becoming very popular, GPT-3, 4, ChatGPT, and so on. And recently, there is a group of researchers that are looking at machine learning for code. Can you use normally LLMs are used for training natural language models, but can you also use them for training against programming languages and use that for various kinds of software tasks? So one goal that we started with was to understand the performance impact of source code changes. Let's say you have a long-running Git repository with lots of history, and you want to see, from commit to commit, when you do different commits to the code or different changes to the code, without running the code, can we try and predict if a change in the code leads to better performance or leads to a degradation in performance? Of course, this was the problem we started with, but then we made the problem more general. Can we try and use machine learning or AI for modeling code? Like I was saying, large language models have become really popular. There's a wealth of source code data available online. You can mine GitHub source code repositories for this data. And there have been several efforts recently in the programming languages and ML communities to find patterns in these large corpora of code for various software-related tasks. You can try and identify bugs by creating language models. You can do performance optimizations. You can try to detect malware and so on. Even more difficult tasks such as code summarization, like providing a piece of code and the model summarizing what the code does, or providing natural language prompts saying, can you write a SAXP code example for me? And then the code writing that example for you. And even such tasks have been done. What we wanted to see was, will all of this apply to parallel code? As most people in this community will be aware, parallel code is significantly more challenging. You have to, there is communication with MPI or OpenMP, and there are different things you have to consider when talking about parallel code. So recently, we have been trying to train a model for HPC code. We start with some pre-trained models. One example is Polycoder. These previous codes have been trained on your standard C, C#, such kind of programming languages and mining data from GitHub. Our goal was to see if we can use Polycoder or an optimized Polycoder model for HPC related tasks. So we had a few different tasks, downstream tasks in mind. One was text generation. So can we do code completion? Let's say if we give partial code, can the language model complete that code? Can we do OpenMP labeling? So let's say we say that I want to add a OpenMP pragma around a for loop. Can it complete the clauses for that OpenMP pragma? And then the other task, which I mentioned earlier, was performance prediction, which is probably a significantly more challenging task. You want to be able to predict the performance of a code or predict the impact of performance changes without having to run the code. So for doing this, we started with a pre-trained model. We fine-tuned that model using HPC source code data. We looked at GitHub repositories and their tags. They tag things as HPC or parallel or MPI or OpenMP. We collected a lot of such GitHub repositories. Many of them came from academic research groups and national labs. And then we used this additional data to fine-tune a Polycoder model. And then I'm not going to show the results here. This is still work in progress, so we're still working on improving them. But I'll just show an example of the kinds of things the model is now able to do. So let's say we give this prompt, which is mostly natural language. I want to multiply a scalar float A by vector X and add to Y. The vectors are of certain lengths, and I want to use OpenMP to compute in parallel. And then we also provide the function signature, and we want to see if I provide this much of code, can the model actually write the code? And actually the model is able to write something like this automatically with all that it has trained. So I think this is very promising. In many cases, we are able to generate correct code. Of course, evaluating whether the model is doing the right thing is difficult, because there can be many versions of the correct code. And you have to check, one, if the code is functionally correct. You have to also check if the code actually compiles, it runs. Is it performant is another thing. So there are many different metrics along which we can evaluate how good is the model doing on these code completion tasks. So this is just like, to show that there are many things we can do with large language models and applying them to HPC, and we are just getting started in this area. And I think there's significant research problems that people can work on. So in summary, in this talk, I talked about two things: how HPC and AI/ML can be synergistic. We can use high-performance computing for significantly improving the performance of training tasks. Asynchrony and message-driven scheduling are key. They can improve distributed training performance significantly. Using non-blocking MPI with GPU Direct performs much better than Nickel on certain platforms. And different advances in AI and ML, such as pruning, mixture of experts, and other new AI architectures that people might develop can be exploited to further improve systems performance. Complementary to that, there is a huge opportunity to use machine learning for high-performance computing. You can use models that have been fine-tuned on HPC data to do performance predictions, performance modeling, and you can also use large language models for code modeling related tasks. What we have found so far is that when you tune these fine models, when you tune these models using HPC data, they perform better than just training on arbitrary code. So I think there's an opportunity to train such models using HPC specific code and then seeing how well they perform. Okay, I think that's all I have for today. Thank you so much, and I can take any questions. Actually, maybe if I have a minute, I'll just take one more slide.
Sure.
Yeah, so this is just to mention the kinds of research we are doing in our group. The key vision in our group is to advance computational science and engineering, in which I include deep neural network training. And we think that requires fundamental research in systems, HPC, and AI and ML. And our research groups works in all of these directions. I talked about two things today. One was the first column here, where we are trying to optimize parallel applications, DL training being one example. And I talked briefly about the third and fourth column, which is data analytics and modeling, and how we can use those to self-tune software systems. All of this work is collaborative. We have a great group of graduate and undergraduate students. And thanks to all of my collaborators, which are too many to list here on the slide. Thank you.
Great. Thank you. Thank you for a great talk. Just as a quick mention, we invite you all to the next presentation, our SPCO BCAS series in 2 weeks. On the 16th of March, we will have the pleasure to see Sudeep Bohra of The Matrix talking about chiplet-based generative inference architecture with blocking floating point data types. And now we will move to the Q&A, so everyone can react with raised hand, and then I will unmute you, or you can put your messages and questions in the chat, and I will moderate them. Okay, if we don't have a question for now, okay, sorry, we have one question. We should be able to speak now, Nabil.
Yeah, so thank you for the great talk. I have one specific question, actually. So the optimized Axon, so when you turn from Axon to Axon++, you mentioned that you perform or reduce operations in sparse format. Mm-hmm. How do you exactly do that? Do you transform them into simple point-to-point messages, sends and receives?
No, actually, we are reducing the amount of data we are sending. So again, this is my recollection, and I think the students with that would have a better idea of what we are doing here. But basically, instead of storing the data itself in dense and sending lots of zeros, we switch to a format where we don't send the zeros at all. So we are sending a sparse tensor in a sparse format.
I see, but how we realize this operation is instead of using, for instance, MPIs or reduce, which is a collective communication operation, mm-hmm. You use just sends and receives, right? So it turns into a point-to-point communication as a result.
As far as I understand, we don't use point-to-points, but maybe this is a question I can get back to you on.
Okay, that's fine. My question was if in the figure in the next slide, which is slide I think 24, you categorize point-to-point communication and you have also collective communication. So my question was if those or reduce operations turned into the point-to-point category, because interestingly, the point-to-point increase as the number of GPUs increase, which is so nice.
So the point-to-point communication is coming from the pipeline parallelism. So we are still doing all of those point-to-point communications.
Okay, all right, thanks a lot.
Great. We have another question from Mikhail. So I'll mute you now.
Thank you very much for a great talk. I have a question in the light of this research for the optimized collectives and for the machine learning. So to me, from sort of historical perspective, it seems that people in 90s, they decided to develop this very unified communication standard like MPI, which sort of covers all of the use cases for like various high performance applications. And what we see now, for example, with this nickel, with your research, is that essentially people try to take like this basic idea of collective communication and tailor it for some particular application. So it's sort of like the history like goes on this spiral again to very specialized implementations. And there was also research, for example, done by Thurston on this quantum MPI to sort of how to provide best interface for quantum computing. So my question is like more, do you envision this trend to expand? Like we will see more application-specific MPI implementations, or like it again will be like people will find optimal APIs somehow?
That's a great question. So again, I think at least for nickel, I think again, I don't know if like the main reasons for why NVIDIA developed nickel and not use something like MPI. But I think they wanted to have something specific for their GPU platforms, which is why it emerged. I think the main reason is for why people go ahead and develop these, one-off messaging libraries and so on, is because maybe the communities do not talk. In fact, when we were working on this, we were surprised that people are not using MPI non-blocking primitives in these deep learning frameworks, right? And we actually talked to someone who works in machine learning, and they said the machine learning community tried these a long time ago, maybe in the 90s, and the non-blocking stuff was not great then. So they were like, oh, maybe this is not the best thing to use. So they switched back to using blocking primitives, and then they never tried that again. So I think maybe the goal should be here for these communities to interact more, so that we can, not reinvent the wheel again and again. And I'm hoping we don't develop like different MPI flavors for every individual problem we have, and we can use, more flexible solutions for different kinds of workloads. I don't know if that answers your question, but.
Yes, thank you very much. Thank you very much.
Okay, we have also one question in the chat from another Martin. The question is, if the natural language model can select kernels that achieve higher performance than other code snippets, then could it be used to predict performance impact of code changes, e.g. as a part of a CI pipeline used to detect performance regressions?
So I think exactly. I mean, that's what was our initial lofty goal, although we are not there yet. But what we were thinking was that, software developers, especially in HPC, they spend so much of their allocation and, your compute allocation on doing CI testing, right? And making sure that your new changes do not degrade performance. So what if we could train an AI model which could quickly tell you if your next incoming change in your Git history is going to degrade performance or improve performance without having to do all of the CI testing? So yes, I mean, the answer is yes, it would be great, but I think there's still a lot of work to be done before we are there.
Yeah, Martin, thanks you on the channel. Do we have any other questions? If not, I have a couple. So what is the natural language processing model that you used in the background of your research right now? What did you use?
You mean for the last part of the talk?
Yes, for the last part of the talk.
We use something called polycoder. Sorry. Yeah, this one.
Oh, I see. Okay.
Yeah, and then we fine-tuned it further with HPC data.
Have you tried the different ones like GPT, and have you explored the other options?
I think we tried 3 different models. Of course, like I don't remember all of the names right now, but again, we were limited by the models that have open source weights, right? In this, so far, we haven't trained models from scratch ourselves. Of course, we can do that, but then that requires significantly more training time, like 3 months to train the initial model and then fine tune with the HPC data. But again, like I've been thinking about, which this is on our mind, like we can connect all of the Axon parallel training stuff we are doing to train things from scratch and see how well that would do.
Great, thank you.
So among the models we tried, Polycoder was the one that gave us the best performance.
I see. Okay, thank you. And so you have only looked really at, I don't know, correct me if I'm wrong, you looked at just giving prompts and automatically sort of parallelizing the code given the prompt, right? So given a prompt summation or something else, give me a parallel code that does it. Have you, for example, looked at intermediate representations of the code and then taken it from there, or was it only?
That's a good question. Yeah, so I think, so first I'll mention that what we have looked so far has been, we were trying to figure out how best to evaluate these models, right? So we came up with these 3 specific downstream tasks. Of course, like there are so many other tasks we could come up with that would evaluate the models in different, along different dimensions. But yeah, I think the question you bring up, actually, someone else has also brought up this question before. Can you start with the IR representation and then train a model based on that? We haven't looked at that yet, but I think that's something we are very interested in.
I see, okay. And then one final question would be, do you think you can bring more performance? So right now what you could do is create sort of normal synchronous code, right? With just an NLP model, and then parallelize it using already existing frameworks, right? So we, for example, as a lab developed DACE, which is a data-centric parallelizing framework, right? And you could just train a model that gives you only the synchronous code, and then we automatically parallelize it. Do you think combining those two in a model like you do, just all machine learning, beginning to end, could bring better performance?
So sorry, I'm not sure if I understood the question. If you already have a model that has synchronous routines?
Yeah, so the idea would be essentially to take your prompt, right? Generate a synchronous code, and then just parallelize it, right? So with a framework that automatically does it for you, not necessarily machine learning based, right? Deep learning based. Yeah, so the question is, if you use NLP model for the whole end-to-end based framework, would it be better in performance, you think?
I think that remains to be seen. I think the first question would be if the model can even handle such a complex task, right? And generate correct code. I think, like I was saying, in terms of code generation, we are still looking at how to improve the model. So there are still instances where it generates like either not performant code or incorrect code. So that there's still like long ways to go in terms of being able to, handle more complex codes and the model being able to like, take an entire framework and then write a parallel code for it.
I see. Okay, thank you.
Okay, thank you.
I don't see any other questions in the chat, or no one's raising their hand. So thank you again for the presentation, and I hope to see you all in 2 weeks.